Good evening, everyone. My name is Sridhar, and I am from Computer Science and Engineering Department. And for AAT Tech Talk on a subject, probability and statistics, my topic is about Bayesian analysis of Bayes theorem. Introduction to Bayesian analysis. Bayesian analysis is a statistical approach that updates probabilities based on new evidences. It is grounded in Bayes' theorem, which relates prior beliefs to the posterior probabilities. This method is widely used in fields such as medicine, machine learning, and decision science. Here, the introduction to the Bayesian analysis, where the Bayesian analysis is a statistical approach that updates the probability based on the new evidences. Which also here can see that it is grounded by the Bayes theorem, which relates the posterior probabilities, and also this method is widely used on the fields where fields such as medicine, machine learning, and also the decision science. Understanding the Bayes theorem. Now let us discuss about the how can we understand the Bayes theorem. Bayes theorem provides a mathematical rule for updating the probabilities. It calculated the probability of a event given given new data based on a pure knowledge. Where you can see here the formula of this is P of A by B equal to the probability of B by A into probability of A divided by the probability of B. Where I can show you this formula is like about the probability of A, which is happening with respect to B, is equal to the probability of B with happening with respect to A, and also multiplied by the probability of A, and all divided by the probability of B. Here, the Bayes theorem applications are many, such as the healthcare, finance, and machine learning, and also marketing and sports analysis. Components of Bayes theorem. Here we can see the probability of A is a prior probability representing the initial beliefs before seeing the data, and also we can see the probability of B with respect to the occurrence with respect to the probability of A, where is likelihood indicating how probable the data is under the hypothesis. Here the probability of B is a marginal likelihood, serving as a normalizing constant. Here we are having the components which are the probability of A, which is the prior probability, and the probability of B, which occurrence with respect to the probability of A, where is a likelihood, and also the probability of B is a marginal likelihood. The concept of prior likelihood and posterior. The prior reflects existing knowledge or assumption before analyzing new data. The likelihood measures how well the data supports a specific hypothesis, and the posterior combines prior and likelihood to give an updated probability after data analysis. Here we can see with an example where the posterior probability is probability of belief with respect to the data, and the likelihood means the probability of data with respect to the belief. And also they're having the prior probability, which is probability of the belief. And also we are having the probability of data, which is normalizes our probability. Bayesian updating process. Bayesian updating involves revising the prior into the posterior as the new evidence becomes available. Each new piece of data can be refine the probability estimates of hypothesis. This iterative process allows for dynamic learning and decision making. Here we are seeing the Bayesian updating, which involves revising the prior into the posterior as a new evidence becomes available. As we can see here, the new piece of data can refine the probability estimates of a hypothesis, and also this iterative process allows us for dynamic learning and decision making. Example, let us take an example for this. It's a medical diagnosis where suppose disease affect 1% of the population and the test has 99% accuracy. Using Bayes theorem, we can compute the probability of a patient who has the disease given a positive test. This example illustrates how prior prevalence influences the post-test probability. Here we are having a example which is a medical diagnosis where the disease affects the population is 1% and the accuracy is 9% of a test, 99% of a test. Calculating posterior probabilities. The calculation starts with the prior probability of the hypothesis. Next, multiply the likelihood of observing the data under the hypothesis. And finally, normalize across all the possible hypotheses to find the posterior. Here we are finding the posterior by normalizing the all the possible hypotheses, and also we are using multiplying this likelihood with the prior probability to know the actual probability of the hypothesis. Bayesian versus frequentist approaches. Bayesian method incorporate prior information while frequentist method do not. Bayesian analysis provide probability statement about hypothesis, whereas the frequentist methods rely on a long run frequency properties of estimators. And also here you can see with a picture showing that here's a chart that shows what you might see if you looked at the mountain ranges through the tennis racket. So here we are having the clear difference between the Bayesian and the frequentist approach. Advantages of Bayesian analysis. Bayesian analysis offers initiative ways to incorporate prior knowledge. It provides a full probability distribution for parameters, not just point estimates. Bayesian methods are flexible and adaptable to complex models and data. Here we can see the Bayesian analysis offers the initiative ways to the incorporate for the prior knowledge. It also finding the full probability distribution parameters, not only the point estimates. Limitations of Bayesian analysis. Choosing an inappropriate prior can be subjected and influence results. Computational complexities may increase with larger models or data. The Bayesian methods require careful interpretation and also validation of priors. Here, let us see some limitations of a Bayes analysis, where the choosing the appropriate prior can be the subjective and influential the result, where we should choose the correct prior, which also helps us to find the result very effectively. And also, the computational complexity which may increase with the larger models or data. Here, which is nothing but we are also saying about the complexity which increases as we take the huge data and models. And also Bayesian methods require careful interpretation and validation of priors. Applications of Bayesian analysis. Here, the Bayesian analysis are used for many applications where we can, some of the applications are which are used in the Bayesian analysis are used in the machine learning for classification and prediction tasks, where applied in clinical trials to update treatment efficiency and also during studies. Employed in finance for risk assessment and decision making under uncertainty. These are the main applications where you can see that we are having the main application which is uh, the classification and prediction of the task using the multi machine learning, and also the clinical trials which update the treatment efficiency during studies, and also which also employed in finance or risk assessment and the decision making under uncertainty. Implementing Bayesian analysis. Here the common tools include software like R, Python, and specialized Bayesian software such as Stan. And also we are using the Markov chain in Monte Carlo, which is also known as MCMC methods, are often used for complex models. Proper model specifications and validations are essential for reliable results. Here, these are the implementations of the Bayesian analysis, which are we are using this Bayesian analysis in many of the programming languages and the softwares such as R, Python, and specialized Bayesian software such as Stan. It also used the methods for the complex model, which is known as MCMC, which is a prominent method called Markov chain Monte Carlo, and also a proper model specification and validation are essential for reliable results. And here we can see practical steps in Bayesian analysis. Here are the practical steps which are define the prior distribution based on domain knowledge, and also collect and incorporate new data to update the model, and also interpret the posterior distribution to make informed decisions. And we are also having the points where you can see uh, where the definition of the prior distribution based on the domain knowledge is most important, and also collecting the incorporate new data update, which also updates the model, which and also we use the interpreter, which are mostly the posterior distribution to make informed decisions. Summary and the key takeaways. Bayesian analysis updates beliefs systematically using Bayes' theorem. It integrates prior knowledge with new evidence to produce posterior probabilities. Despite challenges, it offers powerful tools for decision making under uncertainty. These are some of the references where I could take all this. Where the Gelman A. Carlin is a book which also a Bayesian data analysis are the references for this. And this is all about the Bayesian theorem and of a Bayes theorem. Thank you.